Yeah, thanks very much, John. So yes, well, I'll just, yeah, as John said, I'm Matt Rigby, and I'm here with Rachel and Gareth, who've been working on the OpenGHG project with me. So yeah, I'm gonna give some slides. First of all, just to give you an overview of our project, so you can get a sense of what we're doing, and then we're happy to take questions and discuss some of the broader issues. So I'm hoping everyone can see those slides. Rachel or Gareth, if you can give me a thumbs up, great. Okay. So this is a demonstrator project under the Constructing a Digital Environment program, and what we wanted to do was create a community resource for carrying out greenhouse gas data analysis. And I'll just talk you through initially some of the motivation for why we thought that was needed, and then I'll describe the approach that we've taken. So yeah, first of all, when I say greenhouse gas data, what is it that we use greenhouse gas data for? So probably the most iconic greenhouse gas data set of all time is the CO2 record from Mauna Loa, which I'm showing here. And so this kind of data is used to monitor trends in greenhouse gas concentrations. That's kind of the simplest thing that we do. And there are, of course, measurement stations all around the world producing similar trends to this now. But we also use these data through a process called inverse modeling or top-down emissions inference for evaluating national emission reports. So in the UK, we run, from here in Bristol, we run something called the DEC network, which is a network of greenhouse gas monitoring stations around the country. And so we can use concentration measurements made in the atmosphere, along with atmospheric models and other estimates of greenhouse gas emissions. And we can use that information to work backwards and evaluate the government's inventory reports. So in this figure here, the dotted line are the numbers that the government reports every year to the United Nations Framework Convention on Climate Change. And our estimates from the atmospheric data are in the solid line. And so you can see, over the last few years, there's pretty good agreement between this, what we'd call top-down, this atmospheric data-based approach, and the bottom-up inventory approach. But going back in the past, there's some discrepancies. And so there are questions that now the government are trying to answer on what's causing those discrepancies, essentially. So the UK is one of the leaders in this respect. We're one of only 3 countries that use this kind of information to evaluate our national emission reports. So that's another application. And finally, we use greenhouse gas data of all kinds, so in situ measurement data through to satellite observations, also process models and emission inventories, etc., to try and understand what's happening with natural fluxes of greenhouse gases. So how is the carbon cycle changing? What's causing methane concentrations to change, for example? So that's all great, but what are the challenges of using this data? Well, the first challenge, I think, is going to be familiar to people from all different fields that use especially environmental data, which often comes from very different places in the world, lots of different independent networks and data sets. And really, we have a huge diversity in the type of data that we get. So this is just a snapshot of some of the different types of measurement stations that we have around the world for greenhouse gases. Some of these are laser-based systems, some of them are column measurements, some of them are flask samples that are taken here and there. But as a community, we haven't really come up with a single standard for reporting these data. So we have varied archival standards from all over the world, different calibration scales, etc. And it makes it quite difficult to work with these data sets in a kind of harmonized way. And so when people are publishing particular projects, they often tend to use one network or another, not potentially using as much data or information as they could do. The other problem we have is that these data span very different spatial scales. So these are 2 different satellite products for methane. So a satellite called Tropomi on the top there, and another one called GOSAT at the bottom. And you can see that the Tropomi data is almost like an imaging product. We have this very rich methane data set compared to Tropomi, which is much more sparse. And so there's an issue there of dealing with different scales, but there's also an issue with comparing these satellite measurements, which see a whole column through the atmosphere, to surface measurements, which are just looking at a point in the atmosphere, essentially. And so to interpret these different kinds of measurements, you need to use complicated models that simulate how greenhouse gases are transported through the atmosphere. And so all the different groups in the world who are working on greenhouse gas science, we all have our own different approaches for coupling these measurements and these models together for the various different applications that we're interested in. So this model I'm showing here is something called the Met Office name model. This model shows where the air has been before it was measured. So this is showing the history of the air before it was measured at our UK measurement sites. And so you can kind of get a sense that by coupling this kind of model information with the observations, as the wind kind of blows from different directions, we can start to build up a picture of what the emissions are around our measurement stations. But I think another problem that we have as a community that we're trying to address here is that often, I think it's fair to say, our workflows are not particularly open or reproducible. I think we're doing a better job of providing data archival, although it still has a lot of room for improvement. But there's so much processing and so much analysis that goes on with that data, which is really critical to the results that you get. And more often than not, those processing steps are missing and not available. You'll see in papers that code is available on request, which is and there's no guarantee that if you get that code, you'll be able to run it on your own system to try and reproduce what was done. So reproducibility, open methods for analysis, that's one of the core things that we're trying to do with OpenGHG. So yes, these are our aims. First of all, we want to make it easier to pull data from different types of data archive around the world. Now, it's important to say that we weren't designing OpenGHG to be a data archive itself. We don't want to have to deal with the issue of long-term persistent storage of data or DOIs or anything like that. But what we want to do is provide a set of tools so that researchers can grab whatever data set they're interested in and then pull them into an internally consistent set of standards and work with them, provide some tools that allow researchers to work with them on the platform. So we've developed, along with routines that allow people to pull in data from these different archives, we've developed tools that then can be used to analyze that data. So some of the complicated stuff that often is very carried out in very specific domains with different people with different expertise, we're trying to provide a platform where people can come together with all those different expertise and allow those tools to be used by the wider community. We're also obviously with the standardization, with the transparency of the tools being all there in one online platform, we're trying to make the workflows more open and more reproducible. So the idea is, if you've carried out a certain set of steps in your data processing, you can point to a particular version of OpenGHG to say how you've done that, and then hopefully that your workflow will be replicable by someone else in the future. And another aim was to, once we've got all this data, once we've got this analysis products, we want to make it easier for researchers to show the public or show stakeholders what we've done with that data. So public-facing visualizations is another aim. So I'm going to hand over to Rachel for a minute. So Rachel is a greenhouse gas scientist who's been kind of co-leading the development of OpenGHG. So Rachel's going to briefly talk about how we've approached the issue of standardization and what our approach to code development has been as well. So Rachel, over to you.
Thanks, Matt. Yeah, so as Matt was saying, one of the key things about this tool is that we need to think about how to bring together information from lots of different sources. So we're not trying to reinvent the wheel by coming up with some fantastic new standard that we're expecting everyone to use, but we're trying to find a way to basically bring together data from lots of different sources and have it in some sort of harmonized way so that we can treat it in a consistent way, so that we understand what's in there, what information we're missing, what we need to be able to do the analysis that we're interested in doing. So the first thing is that we wanted to make sure we built on the existing climate and forecast convention. So the CF convention is just a very kind of loose, nice convention about, ordering of information, how information can be presented, the sort of minimal amounts of additional details you need. So kind of quite technical, but really important to make sure that you get those sorts of things right. And another thing was that we kind of learned from experience in our group working with greenhouse gas data that whenever you get data, there's always something which breaks the standard. So we tried to build something which had a very kind of loose metadata type facility in the back end. So rather than thinking every piece of data is always going to have these associated pieces of information, we've tried to make it so that we essentially have a flat database and that you use keys in order to search that and to grab the data that you want to be able to compare that between them. And the routines, as Matt was saying, they're all accessible and transparent because it's all open source. We've got everything available on GitHub. You can go and have a poke around, have a look at what we've done for that. And then we've also tried to make sure that when there are existing data stores, so things like ICOS and CEDAR or some of the big networks or data archives that already exist, we've tried to make sure that we've aligned with those as well. And we are at the moment putting together a publication to make sure that we've lined out exactly what our standards are for this. One of the things as well with regards to this approach is that we wanted to make sure that this standardization, so taking data in lots of different formats and turning it into something that we can understand, was expansible, because obviously we appreciate that anything we write now is not going to be the only things we're going to need in the future. So we're also trying to make sure that we've included an extensible idea within this so that then people can add their own standardization modules, so that if you get a new bit of data in a new format, then you can run it through this as well. And I've also sort of recently been looking at kind of expanding this to being able to interpret things from databases as well. So if we've got big databases of predicted emissions, so like inventories, like Matt was saying, can we use that? Can we put that into our format? And can we do that for lots of different parts of the world related to different sites and things as well? So lots of ways that we can use data that already exists and have that in a format that we can understand how that works. So next slide, if you can, Matt. Thank you. Okay, and as a part of that, one of the things that's been actually really important and I think has been really great about this project is the development approach that we've taken. So rather than just using people in the group that we already had, so people like myself and Matt and other people who already knew about the science, we do have some technical expertise. We brought in Gareth Jones, who's going to be talking through some in the next section as well, as a research software engineer. And research software engineering in this case is the idea of people who perhaps come from a scientific background but have an interest in coding, so they know all the best practices, they know how to make sure that our code is good, to make sure that we're following standards, to make sure that we've got something which is future-proof as well, and also to bring in things like cloud expertise that we don't necessarily have in the group. And so I worked quite a lot with Gareth. We have quite regular meetings where we chat about the code. We make sure that we understand the approaches we want to take. So we're taking that kind of expert knowledge from my side, and we have regular meetings with Matt as well for the same reason. And whereas Gareth can come in and he can take his expertise from that computing side, and he can help us to build a good product which has longevity. And as a part of that, we've also been trying to work with users using tutorial-driven development. So the idea is that you get your users to contribute to tutorials, and you use that in order to understand how to prioritize, how to drive the workflows that you want to create, and how to make sure that you're providing the best features for the users who are going to want to be dealing with and using the product. Okay. So Gareth, was it Gareth going to talk about this?
Yeah. So yeah, thanks, Rachel. That's a great overview. So yeah, Gareth I just is going to talk very briefly about how we've gone about developing the platform itself. So yeah, Gareth, over to you.
Yeah, sure. So yeah, so we started developing OpenGHG as Hugs, which was a one-year project developing like a prototype project, and then we moved to OpenGHG, which is working with Oracle Cloud, which is we use this thing called the object store, which is basically like a key value database within the cloud, and it's very flexible, so you can store as much data as you want, and it's quite cheap and easy to be able to set up and access. Yeah, so we've been developing it on the Oracle Cloud, but we've been developing it in a way that we're using all open source technology. So we didn't want to get stuck on the Oracle Cloud, say if the Oracle Cloud credits run out. So we've been developing it in mind of being able to port it to a different platform. Yeah, so to that end, we're going to be moving on to the Jasmine, one of their new cluster as a service setups. So we're in talks with them to move on to the Jasmine, sort of their Jasmine cloud, which would be good. And because we've developed it in based on open source technologies. It should be quite easy to port over. There's just a few things behind the scenes we need to change. Yeah, and next slide, please, Matt. Yeah, so the interface is mainly through Jupyter notebooks. So these are very good for sort of data analysis. They're very powerful tools. Some people don't like them. So in that case, you can use scripts. You can create scripts. It's just an OpenGHG library you can import, and you can use all the functionality from your command line if you'd like to. But we've developed it so it's based in the cloud, but you can also run it locally. So we realized that people might want to have a local object store. In that case, it's just a file system. You just use the local file system. It's just a load of folders on your hard drive that are used. But the cloud platform, we've tried to base it in the cloud. So it's based outside institutional firewalls. So it's just in the cloud, anybody with an account can access and pull data down and perform analyses and things. But of course, you can also run it on a Jupyter notebook locally, and you should have pretty much the same setup. Yeah, next slide then. So in the cloud, we use serverless functions. So these are nice. You can just spin up a container. Basically, it's like a Docker container in the cloud that you post some data to. You ask it for some data. And similarly, you can do this on a local server or your laptop. So we just segment it out. So you have something that needs to do some computation. So whether that's in the cloud, a serverless function, or your local computer, behind the scenes, OpenGHG will just work out the environment it's running in. And if it's in the cloud, if it's on, say, our OpenGHG Hub, which is a Jupyter Hub instance, it will go to the cloud serverless functions and ask them to perform some action. Or if it's run locally, you'll just be your computer or workstation performing that compute. And so behind the scenes, we have quite a few different sorts of modules within the OpenGHG library. So we have standardization, searching, data comparison, different workflows for working with lots of different types of data. And we've worked quite closely with quite a few of the members of the ACRG group in Bristol to sort of work out what users want from the system and what kind of workflows that they use every day, and how we can make their life easier by having, easily search for data. You can pull data down. It should be quite quick and easy to access different types of data and perform different comparisons. So we try to make it a platform that contains a lot of metadata. So we store all the data just as binary data. So that's compressed netcdf files that people are probably quite familiar with. We're actually looking at moving into ZAR, which is a relatively new format, which is based on most of its HDF5 behind the scenes. But that's also very useful for applications within the cloud, and there's good compression and rich metadata storage and things. And we try to ensure that everything's CF compliant within sort of reasons. And when you search for data, all the units, calibration scales and everything come down with the data. So you should be sure of the data you're getting, where it came from, who you need to cite, etc. And yeah, so behind the scenes, when you're performing all these actions, it's OpenGHG. If you're running it on the OpenGHG Hub, it'll be asking the Oracle Cloud object store for data. So this is just, I've got a picture of a bucket here because within object stores, they like putting data in buckets. It's just some terminology. So it's stored in the cloud, or if you're running it on your local machine, it will just look up data on your hard drive. And we're also implementing a way of having sort of a local object store on your computer. Say if you want to do play with some data, you may not want to put on a public or your group object store, but you can also then have access to a group object store. Say if you want to just run this internally, you can have it on your, data storage facility somewhere, or you can run on your local hard drive. But also we'll be running the OpenGHG Hub, whereby you can access all the data that's stored within our object store and perform analyses and things using cloud compute, whether that's Oracle, but probably moving forwards, that'll be within the Jasmine cloud. So yeah, I think that's me.
Great, thanks, Gareth. So yeah, as Gareth said, that's what the back end is doing. This is just a quick visualization here of what the user experience is like for researchers who want to use the platform. So as Gareth said, we're using Jupyter notebooks, which users will, I'm sure a lot of people here will be familiar with. So the point is that where the researcher is running locally on a group server on their workstation or in the cloud platform, we wanted to make sure they had the same experience essentially. So that's what's provided by Jupyter notebooks with the various different backends that Gareth was talking about, depending on the platform you're working on. So here, this is just showing a little workflow where a user is pulling down two different data sets and just quickly plotting them up against each other. So as Gareth said, all of the software we've used to build OpenGHG is open source, and the project itself is completely available on GitHub. And the hope is that if we can get the community invested in this project, then that they will be able to extend the code base themselves or find errors, etc. So we're just at the phase now of kind of starting to roll this out to other people and other groups. And so hopefully, if we can get some buy-in to this, then it will become more than just our efforts here in Bristol, and it will become a community product that people can use. So one place where we've already found a lot of value from the OpenGHG approach actually is in the outreach and public engagement side of things. So once you've got all this data into a standardized format, ideally somewhere in the cloud, then you can start to use it to show people, to showcase your data to the public. And so we tried this out during COP 26, which was in Glasgow last November. And what was happening at COP was that lots of different groups from around the world were coming to Glasgow to make greenhouse gas measurements as a way of showing policymakers and the public what we could do with greenhouse gas data, and also obviously make people think about their carbon footprints, etc. And so there were groups from Berkeley, Bristol, Royal Holloway, National Physical Laboratory, a few other places as well, University of Cambridge, all came together with a whole variety of different measurements, as we've said, all on different standards, different calibration scales, etc., etc. And so, we merged all that data into OpenGHG, and then built a dashboard, which I'm showing here, which allowed the public to take a look at some of that data. So, it was a nice way for these different groups to showcase what they've been doing. This is just showing what the measurements actually look like, but it also provides a nice interactive way of getting users to start to understand why we're bothering to do this. So on the screen here, we're just showing some explanatory material talking about how we use this kind of data for evaluating the UK's greenhouse gas emissions, for example, and why that's useful and why we might want to do it. So this dashboard that we made it was made for COP, but it's been made to be easily modified so that other groups can quite simply change the front end for their own projects. So we're hoping that this becomes a useful end product for other projects as well. So just finally, I want to start the discussion soon, but something that's already kind of grown out of OpenGHG is some machine learning tools that we've been developing. So one thing that I alluded to at the beginning is that you need quite complicated, quite computationally expensive models to help interpret the data. So I mentioned the Met Office name model. That's a model that we use quite a lot here in Bristol, but there are other types of model out there that do similar sort of things. And what these models do is they estimate the footprint of a particular data point. So in the plot on the left here, you can see that this is a zoomed in view of this footprint. What it shows is the areas of the surrounding surface which influence a particular greenhouse gas concentration. So if you have emissions in any of these red areas here, it will strongly influence your data point. You'll see an enhancement in the concentration due to those emissions. Whereas if it comes from the surrounding regions, you won't see it. And so with this kind of information combined with the data, you can start to learn about emissions. But what we were finding is that it's a very slow, computationally expensive approach to work out these footprints using a three-dimensional model. And so if we're starting to think about integrating all these different data sets, and especially satellite data, we're going to run into computational bottlenecks quite quickly. And so we've been looking at the idea of using machine learning to help try to accelerate this process. And so we do it by taking meteorological inputs directly. And then in this case, we're using gradient boosted regression trees to try and emulate what these footprints are given a set of meteorological conditions. And so you can see, so what we've done in this case, I think we trained the algorithm on footprints and meteorology from 2014 and 2015. And then on the right, you're showing an emulated version for 2016. So the 2016 estimate hasn't seen any footprints for that year. It just knows about the meteorology. I think I have an animation. Yeah, so you can see this gives a sense for what these emulated footprints are. So the true footprints are on the left and the emulated version is on the right. And so yeah, so we've been quite encouraged. This is a relatively straightforward machine learning algorithm, but it shows some promise that we think we can start to use these machine learning approaches to help solve one of these bottlenecks. So this is now spun out into a Google PhD fellowship, which is building on this, and hopefully this will become a service that can be provided to users through the OpenGHG platform if we can work out some of the finer details. Just to show that it doesn't just work to make fancy plots, it seems to work in practice as well. So this is a methane simulation, methane concentration time series that's made using the emulated model versus the real model. So the real model is in blue here, and the emulated model is in orange, and we seem to get fairly good agreement at most of the sites we've tried this at. And crucially, I guess, when we try and work out emissions using these footprints, so these are UK methane emissions for 2016. The emissions that we infer using the true footprints is in blue, and using the emulated footprints is in that kind of greeny color, and we get comparable estimates. It's clearly not perfect, but it's it's within, most of the time it's within the uncertainty in the method itself. So there's some mileage there, and we're trying to think about how we can improve this and how we can take it kind of global, essentially. So yeah, I'll stop talking, and I'm happy to take questions. So there's a lot more detail on our project available on our websites. We've got we've put quite a lot of effort into the documentation and the tutorials, which are there on the web, on the website, and also on we're trying to build up a portfolio of tutorials on YouTube. So we're doing that. So yeah, so I'll stop talking, and I guess John, are you gonna field the questions here, or would you like me to do that?
Yes, no, thank you, Matt. Yeah, I'll take care of the questions. If people listening to the webinar would like to ask a question or just make a comment, and it's meant to be fairly interactive, then please put it in the Q&A channel, and I'll put those to Matt and his colleagues. So thank you, Matt, for a really interesting talk, and also to you, Gareth and Rachel. I have a couple of questions already in. So John Huthnants is asking, what is your relationship with the Copernicus atmospheric modeling system? And maybe you'd like to explain what that is for those who may not know.
Yeah, so the Copernicus atmospheric monitoring system is a European project to evaluate greenhouse gas emissions, primarily using satellite data, although it's not exclusively so. I mean, what's our relationship? I mean, it's the stuff we're doing here in the UK is fairly independent of CAMS. We have our own UK focused greenhouse gas evaluation network, as we said. But ultimately, yeah, I mean, we're going to be moving to integrate what we do, or to, the things that we've learned from our UK experience. We're in communication with the CAMS folks, and we will try and make sure that scientific developments speed up that way. In terms of the OpenGHG project, I mean, I know there are European projects that aim to provide some elements of this kind of open data analysis framework. CAMS itself doesn't have much of that, as far as I'm aware, although there may be some data viewers and things like that. There is another big European project called ICOS, which data from which feeds into CAMS. They have a particular set of data viewers and kind of Jupyter-based data analysis systems that work focused on ICOS. And the US also has some of their own little pieces as well. So yeah, there is this ecosystem growing, I guess, of projects which have fairly similar aims. We're trying to make ours, I guess, what's the word, as flexible and as extensible as possible. We're not focused on one particular type of project. We're just trying to focus on the main issues that we know that all greenhouse gas researchers are going to face. And we're trying to build the code in a way so that it is interoperable with these other systems. So I mentioned ICOS. We're trying to make sure that our code and our standards are comparable with what ICOS are doing, so that users can hopefully use both. But yeah, it's going to be an interesting few years, because we're not the only people who've identified this problem, and I think it's good that there's a diversity of approaches out there, and I'm sure some projects will end up being used quite widely, some less so, and we'll just have to see what the community says over the next few years, I think.
Sure. Yeah.
We did have a chat with the people who run the ICOS data, the COM portal, right? So yeah, so they're very much involved in discussions, and we've communicated with them, because they've obviously had quite a successful platform, but it's very specific to this European network. So it doesn't have this kind of idea of bringing in lots of different sources from different places. It's very focused on this ICOS European network. So it works really well for that. But we're obviously trying to take their data and see if we can make that so that it's more general rather than focusing on one specific network.
Great, thank you very much. It's not in the Q&A channel because it's Kriti who's on the panel. She's asking how much uncertainty you see when handling data from different sources, and how do you handle it? I guess, Kriti, you're probably thinking about if data formats change outside your control, that sort of thing, or if new data sets become available. So I don't know who's best to answer that, but
I don't know, Rachel, do you want me to start answering that, or would you like? So uncertainty, yeah, I mean, I don't know what to say really. Yeah, one of the issues is that there are the data all have different uncertainties, different calibrations. Some data is not calibrated at all, and so I think all we can do from the point of view of the platform is make sure that we're taking in as much information as we can on the uncertainties, on the calibration scales, etc., that these different groups have used. And really then it's up to the scientists who try and interpret them to figure out how those come together. But yeah, it's a problem with our field. It's difficult to account for these uncertainties. It's difficult to propagate these uncertainties into the products that you're aiming for, like national scale emissions or whatever. But from the point of OpenGHG, we're just trying to make sure, we've set a standard where you have to tell it, what your uncertainty is, and we just make sure that's all documented and the metadata describes it appropriately.
Yeah,
I don't know if that answers the question, but
hopefully. Right, so another question from the audience. Louise Darroch has asked, is it possible to integrate data with other networks or other users of the platform? For example, have you considered the use of vocabularies in CF, NetCDF files, or object stores to make the data interoperable?
Yeah, I think the answer is yes, but Rachel, I see you nodding. Do you
yeah, so obviously we've also, Gareth spent a bit of time building tools to integrate other network data. So we've got data that obviously comes from measurements that have been made from some of our colleagues at Bristol that we've integrated. But generally what we've done on the platform is we've tried to find ways to integrate public access data. So that means that we've integrated with pulling down data from the CEDA archive. So there's quite a few, so that's generally quite a standardized format. So we try to adhere to that format as much as possible. And I believe Gareth put in a CEDA checker as well to make sure that our data is CEDA compliant. And we've also integrated with the NOAA data as well. So we've got some tools that can take the various different NOAA OBS. So NOAA, just for reference, is a global network is it American standards that are generally applied, Matt?
Yeah.
So it's kind of compiled by American institutes, and then that's then put together, so data for different greenhouse gases, and then those are kind of periodically released, and they've got quite a lot of really nice metadata in them as well. And so what we've tried to do with that is, again, we'll make sure that it has, as a minimum, the amount of information that we need for our platform, but we're not going to just throw away information if it's been provided. So if data has come from the NOAA network, for example, then we've generally tried to retain any additional information that they put with us. So largely, if we're getting data from different networks, we're trying to make sure that we're not fundamentally changing the data that's been given to us. We're trying to make it so that it still adheres to the standard that they've applied. It's quite a light touch standard in that way. It's just making sure that we have all the information we need so that our tools can understand what's available. So I say that it's pretty well integrated in that way, because we have obviously engaged with several networks already. I'm sure if we were to engage with more networks, we'd need to have a think about making sure they were integrated in as well. But it is something we've put a lot of thought into.
Yeah.
Okay, thank you. I've got a question from the panel. This is from Cameron Ross from NERC, who's asked, you've built a multidisciplinary team with Rachel as a GHG scientist and Gareth as a research RSE. I'd love to know what benefits you'd say that has had for your work. Were there any challenges you had to overcome to get a mutual understanding, for example?
That's a great question. I will. Maybe I'll start, and then I'll get Rachel and Gareth can have their perspective as well. I think. So yeah, I mean, there are enormous benefits of working like this for sure. I mean, as Rachel was saying in the presentation, you know, me and Rachel have spent years building this code that does a very specific job. But once you start to think about making that code available to the outside world, as everyone here who's tried to do something like that knows, suddenly you realize how limited your coding skills are in some respects, how limited your how wanting things like some of the research software engineering standards are that you use, you know, the standard of version control, the standard of documentation, etc., etc. And so it's been great to get a proper professional in the room to kind of help us, you know, whip our code into shape that is not only works better when we're having to apply it to all these different situations which we hadn't thought about before, but also just make sure we're following the best practices that we can, which then has a huge benefit for future proofing, right? You know, we have some confidence now that if you know, if something happened to one of us and we had to leave the project, for example, the code is in a really good state, it's well tested, and it's in a position where someone else can potentially read that through, get up to speed on it quite easily, and be able to fix problems in the future. So yeah, there's a clear benefit there. There's also been a huge benefit when we're thinking about trying to put this on the cloud. That's obviously way beyond mine and Rachel's expertise, and it requires a whole new way of thinking, a whole new vocabulary that we don't have, and so that's been you know, that's been a huge benefit of bringing Gareth in to do that. I think one thing I would say about the challenges is that you shouldn't, you can't underestimate the time that it takes to get both communities on the same wavelength. You know, which is why I think the approach of Gareth and Rachel working in parallel has been essential. You know, it's not like you can just say to a new research software engineer who may have been working on something completely different the week before, right, here's our idea, go away, generate this product, give it back to us, because, you know, it's almost impossible to communicate all the nuances of what we need. And so it's required an awful lot of trial and error of me and Rachel saying what we think we want, Gareth trying to put it into practice, us realizing that actually maybe that wasn't what we wanted in the first place, and perhaps we should have tried a different approach. And so it's been an iterative process, but it's yeah, that's my perspective. I don't know, Gareth, from the research software engineering side, what do you think?
Yeah, it's been really good because, you know, because my background is computational biology, so coming into like an atmospheric chemistry group, like for quite a few meetings, I was just, you know, but it's been really, I think, really well, it's just really good having working with Rachel so closely and being able to just like throw ideas at each other and just
like we have discussions about stuff and we kind of talk it through, don't we, sometimes for the design.
Yeah, and like things can, you know, I've got an idea about something, and then I think it's really good. I think our brains work in quite different ways. So I'll come up with an idea, and Rachel's like, oh, why would you want to do it like this? And then we sort of like bounce ideas off each other until we get to a point that, you know, we can start. And then even if we, you know, write a function, write workflow, and then find out, you know, a few days later that we can just go back and have a chat again. And like, you know, I think it's that, not trying to sort of over plan things and just sort of like work quite iteratively. And then I think where this is where this like tutorial driven development kind of idea works quite well, that if when you're writing tutorials for, you know, code that you've written, because you're so close and you know what's going on behind the scenes, it's not until you sort of put yourselves in the shoes of a user that you can be like, oh, actually this interface isn't very nice, or this is a bit of an awkward way of using it. And then, yeah, if Rachel uses a function that I've written, like, oh, this is a bit awkward, or the documentation is not very good, and then we can just go back and open an issue on, you know, on our repo and things. And yeah, just as I said, throw ideas back and forth. It's really, yeah, really valuable. Yeah,
and one thing I would say is that I definitely feel very upskilled from working on this project, because it's not, I think with a lot of people who work on these sorts of things, it's not that we don't have the capability, we just don't necessarily have the time and resource to kind of go off and learn what's cloud do, how do I write things in a specific way. And I feel like if you're slightly more computationally oriented, then you have the want, you just don't always have the will. And so yeah, so working with Gareth and seeing the way that he's approached things and the tools that he's used, I definitely feel like it's upskilled my abilities, because we've worked quite closely together. I've contributed quite a lot to the code now as well, but I've done that based on the framework that he's built and then learning the ways that he's approached things. And then that's also benefited me in some of my other research and also on some of the other work I do as well. So it's really beneficial to have this close relationship with someone who knows what they're doing, and you feel like you can bring to it that kind of expertise as to, well, I think from a scientist perspective, we look at it like this, whereas he brings in a kind of but from a research or from an engineering perspective, we look at it like this. Yeah. And so, yeah, and I think I feel like I've benefited a lot just from having a person around who knows what they're doing. And so I've learned from reading the code and feel like I'm a better coder now because of it as well. And that helps with all aspects of my work.
Great. Thank you for a very full answer to that. That's brilliant discussion.
I think we like talking about it.
Yeah. Right. Oh, we've got questions coming thick and fast now. So Matthew Haynes is asking a question about validation. So has the name model or your ML model been validated in some way against real world CO2 observations? And if so, do you know where it has limitations? Could you use real world observations to improve the ML model that you have developed?
Well, I better try and give a brief answer to this, because I could talk about this for about 2 hours. The name model itself has had some level of validation, but you'd be quite surprised, I think. You know, what we do to evaluate these models is we release a known amount of some tracer into the atmosphere and take samples downwind to see what the concentration are. There are other things people do as well, but that's kind of the main one. But that really has only been done on quite a campaign type basis, and actually not for quite a while. So it's definitely something we need to look into. You can't really use CO2 observations because you don't really know what the fluxes are, which is the big problem. In terms of the machine learning model, you know, because we're training against the 3D simulator, the algorithm can only ever be as good as the model itself. So that's going to be the limit there. Ultimately, we need proper validation, or improved validation, I would say, of the 3D simulators. But in the meantime, we're working on a machine learning emulator that's going to try and get as close as we can to the 3D simulator.
Brilliant, thank you very much. So we've got a couple of questions on basically sort of the infrastructure. So Adam Varley is asking a question to Gareth particularly. He says the project he works on aims to combine satellite and sensor data in nearish real time. We're also working towards using a cloud provider. Have you got any advice on which providers to go with, particularly within a research or education setting? And what are your experiences in terms of operating interoperability, OGC, standards like Sensor Observation Service. And he also adds a comment, great work, guys. So, Gareth.
So I don't, well, we've worked with Oracle because, well, well, I don't really want to, shill for Oracle, but they are quite good as long as you kind of, I think, know what you're getting yourself into, at giving researchers cloud credits and things. Now, of course, there's a company and they want things back, but it might be worth getting in touch with them. There's quite a nice guy, Richard Pitts, who might be worth having a chat with, Oracle, and I think he was in a previous life, he was a researcher, and so he's quite interested in supporting researchers, and if it's a sort of satellite greenhouse gas, that sort of fieldish thing would probably go down quite well. But I think a lot of the cloud platforms are, well, we're absolutely fine. Jasmine, if that would be under Jasmine's remit, that could be worth looking into. But one thing I would say, if you do get cloud credits, think about how long your project wants to run for, and if you'll use the amount of cloud credits, because sometimes you'll hit barriers, say like you have £5,000 to spend in a year, and after that year's up, even if you haven't spent the money might disappear. So think quite carefully about how the credits and things work. But I think, in sort of technical aspects, most of the clouds will probably be pretty good. But it's probably definitely worth getting in touch with whichever one you're interested in and asking if there's some kind of, researcher discount, something like that. And then
I think if I could just chip in quickly, I think from my perspective, when we were trying to look at, which cloud providers to use, as Gareth said, technically they all seem very similar, and cost-wise, I couldn't really see any, huge difference. I guess the ultimate, I don't know what kind of satellite data you're talking about here, but ultimately, the challenge that cloud would solve, at least for researchers, is having the data and the compute be in the same sort of place. So if you are looking at a big satellite data set, I guess ultimately what you want is to have your processing, your comparisons, whatever, happening on the same cloud service as where the data is stored, so that you don't have these enormous, data upload or download issues. But I think either way, we do have a kind of a bit of an issue, really. If we do want to use cloud more widely, it does pose some problems, as Gareth was kind of alluding to, for research projects, because ultimately cloud providers are essentially expecting a credit card that you can put behind the bar with them, and they'll charge you when you use it. If you don't use it, often you have to buy a lot of these credits in advance, and you'll lose your credits. And so we do need a kind of a solution that has longevity. And we're trying to look at the Jasmine cluster as a service, as a way that we can have kind of persistence in our cloud, platform. But I think it is something that the research community and the funding community needs to think about, really, because there's a lot of potentially very big benefits, but it is challenging, I think, for the way research funding happens at the moment.
Great, thank you. Got one more question from the audience. So if anybody else, we've got about 8 minutes left, so there's time to sneak another couple of questions in. But Neil Humpage has asked, as a data provider, do you have any advice or suggestions for best practice when it comes to formatting and storing our measurement data to make it more easily integrated into the OpenGHG system?
Well, yeah, maybe Rachel can answer that, but I'll just say hello, Neil. You're one of the data providers we're hoping will use the service, so that's good to see that you're online.
So which data service does Neil represent, just for those of us who don't know?
Well, Neil is at Leicester, and he's got a great data set of upward-facing Fourier transform spectrometer data.
Okay.
Yeah, that's looking really nice. Yeah, well, the first thing is, I guess, ideally it should be on a public archive with a DOI, so that we know where to look for it, and hopefully one where it's easy for us to be able to automatically read the data. But then, I guess the Well, the first thing I would say is make sure that you have your own internal automated processing of the data. One of the most frustrating things for us actually is when there's clearly some manual processing of data that happens by the data provider. And it often means that you get different problems with the data every time you get it. So sometimes you get a data set, you'll tell them, hang on, this time format is not readable by a computer, or this column needs to be there or something, and you'll go back, you get the data again, and then you get a different set of problems with it because they've had to do some clicking in Excel and forgot to click it in the same order as last time. So I'm sure Neil does this, but make sure make sure you have scripts that automate that processing yourself. But then from my point of view, it's just making sure that all the metadata is there, and that it's descriptive enough of the data that we can make sense of it on the platform. But Rachel, I can see you're looking to chip in as well.
Sorry, I just wanted to mention the schema thing that we set up associated with this, because that could kind of answer the question. Yeah, so basically, and I need to kind of write a new tutorial to demonstrate this. The way that we had to kind of categorize the different data types, as we call them. So we've got things that kind of look similar to each other. So we've got sort of surface sites, so things like in situ measurements, flash measurements, tower measurements, and they all kind of look similar enough that we kind of categorize them as one data type. For the TCON data, we've got something called the column type, and that covers satellite data and data kind of going up through the atmosphere. And this isn't quite finished yet, but basically what we've done is on each of those types, they have an associated schema for them. So the way we internally store the data is as netcdf. And so what that schema does, it basically tells you all of the different like variable names you're expecting. And I need to sort of tweak it as well. So it should also tell you all the different metadata that we need. And so if you go and grab the type that's associated with the data you want to upload, you go and look at the schema, then that should give you the information about how, what we need in order to be able to integrate that into OpenGHG. So it doesn't have to be netcdf, but as long as you have that information, and then, so if you could do it as netcdf, that would be ideal, because then that could just be a straight, we understand this, we can put this straight in. But we do need to kind of finish up some of the details around that, but that's just something I thought I should point out. If you want to know how to make it easier to integrate, then you can go and have a look at that, and then that should define, it's quite a loose format, as I said, but the kind of minimal information that's needed in order to be able to, for OpenGHG to understand it.
Yeah, and so we and Neil, by all means, get in touch with us, or maybe we'll reach out to you, because we, as Rachel said, we are formalizing the schema for that type of data, and so we want to make sure it's useful to you guys as well. So we should have a chat about it.
Thank you very much. I just have a couple of short questions from Kriti, as I don't see any more audience questions. She's asking how much programming skill is required to be able to use your platform, the OpenGHG platform. First one.
Yeah, well, that's a good question. I mean, one of the main motivations for us doing this is that greenhouse gas data analysis very quickly gets very complicated, and so we wanted to remove a bit of the pain, from people, for example, who know how to make measurements but then don't necessarily know about how to use the models. We wanted to make that a bit easier for people like that, so you don't have to have a huge background in computing to be able to do it. So what we're aiming for is to be able to do some basic data visualization and analysis. You just need to know a little bit of Python ultimately, and then obviously understand how to use the different routines in OpenGHG. So that's the aim. And then obviously, if you want to do a more advanced, more rich data analysis, you will inevitably need some more coding skills. But to do the basics, hopefully you would just need some fairly simple Python experience.
Great. Thank you very much. And the other question, final question I think we've got, is also from Kriti. She says, what happens in countries where there aren't many observations? I think when you showed your map, there were some quite notable gaps. I guess it's not really a question for your project so much, but I suppose could your project enable more data to be added to it? So perhaps a project that doesn't have an infrastructure of its own, could you create a data format that they could contribute data, for example? Yeah. So we do have huge gaps around the world. For CO2 and methane, the satellites are starting to fill those gaps a bit. But for a lot of gases, there's no substitute. You need to have in situ measurements, and ultimately it does need infrastructure on the ground. So we can't really help with that. But what I hope we can do is help researchers in those countries
more quickly make use of the data when it does become available. You know, that's what we hope we can do. You know, you'll be hopefully very quickly be able to look at your data, visualize it, and then also see how it compares to the global networks, for example, which is a really useful first step in your processing chain. You know, if you're way off compared to NOAA or A-Gauge or one of these other big global networks, you know, you might have problems. You can go back and look at your instrumentation. But yeah, so we ultimately it needs data on the ground, but we can hopefully help once it's there.
Fantastic, thank you. Well, we're now fast approaching 12 o'clock, so that's the end of our hour, but I think it's been an absolutely fascinating discussion. I've certainly learned a lot about the project. That was what we were hoping to do, and we've had a good number of attendees and some really interesting questions, so I think it's been well received. So thank you very much, Matt, Gareth and Rachel. You know, we'll hope to hear more about your project as it continues. I'm sure we will. So just now a plug for the next webinar. That will be on the 11th, so in 3 weeks' time, 11th of November, when Steve will be interviewing Dr. Jenny Brown and her team about the Cream Tea project. For those of you who don't know, Cream Tea is about coastal resistance alerts and monitoring. So that will be fascinating, I'm sure. As with all of our webinars, this one has been recorded and it will be going on our YouTube channel within the next couple of weeks. So if you came in partway through and would like to catch up on it, or if you want to share it with one of your colleagues, then please do catch up with that. And I see that Cameron has just put the link in the chat, so please do that. And we hope to see you at the next one. So thank you very much and goodbye.
Thank you.